So good afternoon, ladies and gentlemen. Welcome to the meeting of the Nečas Mechanics. So our today's speaker is Professor Pablo Pedregal from Universidad de Castilla-La Mancha, Ciudad Real in Spain. So Pablo has been working for many years in the area of calculus of variation and partial differential equation. So those of you who have ever worked with Young measures, they know this famous characterization of gradient Young measures by Kinder and Pedregal. So this is the part of the couple. So and today we will speak about some non-local programs in the calculus of variation.
Thank you, Martin, and thank you for such a kind invitation to be back to Prague after so many years. To see again many friends and colleagues. It's been my pleasure. My intention with this talk is I would say, very modest, in the sense that I would like to try to persuade you that if you push non-locality far enough, then things can become a bit different compared to what we are used in the local, traditional, classic calculus of variations. So I will try to convey that message in simple terms, just looking at very simple examples. Although I will also discuss some general setting, so that one can argue or one can try to extend those simple examples to more complicated situations. You know that non-locality is everywhere today in analysis. Apparently, a lot of people working in non-local versions of almost everything, right? And at least for me, there are mainly two areas where non-local variational problems are playing some significant role. One is the application of variational problems to continuum mechanics in the context of peridynamics, and there are some issues there, both versions of bone-based peridynamics and state-based peridynamics. And for those of you who know a little bit, there are some issues there concerning the finite horizon situation, where you have to restrict attention, or where you would like to deal with limited domain, a bounded domain. You can also have to pay attention to boundary conditions, and again, in this non-local context, you need to treat some sort of non-local boundary conditions, so to speak, right? And of course, you have to pay attention to non-local gradients as well. That's part of the passage from local to non-local. And there are also some interesting image denoising models, where again non-locality apparently is playing some role in trying to push those models. So, but you also know that even in the more general context of PDE, there is there is a lot of work. I mean, an immensely large amount of work on PDEs and non-local PDEs of every sort. Of course, starting from the fractional Laplacian and looking at these Gagliardo-Sobolev spaces and many more generalizations in the PDE context. They are trying to extend typical results in the traditional local situation to some non-local versions, even at the level of obstacle problems, the classic obstacle problems. They are trying to extend those to some non-local versions. So optimal control problems, they are also looking at optimal control problems from the point of view of non-locality. So almost, I would say, almost everybody is trying to extend or to come up with versions of known results to the non-local situation. So for me, the non-local variational problems that I would like to look at are of this form. Here you see that that here we have this non-local gradient Vs, which essentially I will not get into that because this is something rather delicate, I would say. But what I would like to point out is that this DS is some sort of non-local singular integral linear operator, similar in some sense to the classic local gradient. And so when one looks at these variational problems, which look formally the same as the traditional or the classic situation, one would tend to believe that there should be something new coming out of this model. So because this DS, this non-local gradient is something different from the local situation, one would wait that, or one would look at the main issues as in the local case, and one would try to understand Willow semi-continuity or quasi-convexity, for those of you who know, or and then existing theorems for these kind of non-local models, or the Euler-Lagrange system of optimality. I mean, the appropriate envelopes, the relaxation theorems, and all that. And one would have to look at all these questions in the context of this non-local model. And what one would expect is that one would get something new, something different, in some sense. So one would wait for a different concept of quasi-convexity. Why not? I mean, I suppose it's natural to wait for a different concept of quasi-convexity, probably a more general one, more different kinds of Euler-Lagrange equations of optimality for these non-local models. Of course, different formulas for the corresponding envelope. So one would wait that everything would be different in some sense. But the surprise is that that as a matter of fact, it is not, or at least not as different as one would expect, in the sense that the non-local, the appropriate notion of quasi-convexity in this non-local context turns out to be equivalent once one reinterprets that non-local quasi-convexity, turns out to be equivalent to the classical quasi-convexity. And after all, the main reason, as far as I can tell, I mean, just summarize the whole thing in a single sentence, is that after all, this non-local gradient is just the local gradient of some transform of U, where this TU is essentially some convolution operator with the Riesz potential. So therefore, it turns out that the non-local gradient is actually the local gradient of something else. And because of that funny property, it turns out that non-local quasi-convexity is essentially equivalent to the usual notion that we have been looking at for so many years. Of course, this is a long story. I'm just making a long story very short, but in some sense, this is the underlying line, right? And I have just mentioned here a few people. There are many, many more people. These are just the colleagues whose work I'm most familiar with. Carlos Kreisbeck, Heidi Schomburger, Carlos Mora Corral, Jose Carlos Bellido, and Javier Cueto. But essentially, there are a lot of people, a lot of teams, research teams working on these models, from both sides, from the side of mathematics, analysis, and from the side of mechanics. But because I wanted to come up with something really new, some result which would be different from the classical ones, I had to push non-locality a bit further. And in order to motivate this, this non-locality, how one can push non-locality further, let me just try to motivate it very simple examples. And those are the following. So this is the local model, a typical local model where the exponent P, I have just written there P greater than 2, because of technical reasons. Just think of P as being exponent 2. This is a very traditional, simple example of a functional. And I can look at the minimizers, or I can look at the variational problem trying to minimize this energy under typical boundary conditions. Of course, this is so simple that it doesn't require any further comment. But I would like to look at this non-local version of it, which is, in some sense, is like something natural. Okay. So I replace the usual derivative y prime by this incremental quotient down here, but I integrate in both variables x and y. Okay, and I look at the same problem under the same boundary conditions. I would like to find the minimizer, if there is such a thing, for this functional under the same boundary conditions. And you know that these three questions are very basic for the local problem. Whether are there minimizers for the one up there? Of course, there are. If so, the linear function is a minimizer. Of course, that's the unique minimizer up there. And we also know how to write optimality conditions for the local version. Now, I would like to investigate whether the same answers are valid for the non-local version of it. Are there minimizers for this functional? I don't see there is any reason to suspect that there wouldn't be such a thing. Is the linear function a minimizer? I don't know. What else could be a minimizer of such a functional or such a problem? And what about optimality condition? Well, that I don't know. Optimality condition, if there is a minimizer for such functional, the form of optimality condition, I don't know. That would have to be investigated and see what kind. I mean, the form of those optimality conditions, right? So I don't know the answer to these questions for the non-local version of it, and therefore I would like to investigate that. Even more than that, we also know that this example, this is the celebrated Bolsa examples where you don't have minimizer because of the non-convex dependence on the derivative. And if I write the appropriate under the same boundary conditions, the same endpoint conditions in this case, so if I look at the non-local version of it, replacing the local derivative u prime by this quotient over here and integrating y and x, do I have minimizers for this problem? Again, under the same boundary conditions. Again, the only evidence we have is that for the local version, we do not have minimizers. Why? I mean, there's no reason why one would wait that they're going to be minimized for this non-local version of it. I don't, at first sight, I do not see any reason why one would wait minimizer for that. So we would wait that there wouldn't be minimizer for such a function. So this is the version, and here I have just the same functional without this term over here, and we know that for the local version, if we just drop this contribution here, we know that then we have infinitely many minimizers, and I'm just asking whether that would be again the same situation for the non-local version of it. All right. So I would like to give you some answers to at least to some of these questions. But I can place everything in a more general context. So suppose, and this is based on experience with Young measures. So everyone who is familiar with Young measure will, I believe, will better understand what I'm going to talk about next. So suppose we're given a model domain in Rn, R2, for instance, or even R. Dimension 1. So the two main ingredients for a non-local theory, I need a rule to assign to every point in X and every measurable function from omega to Rn. I need a rule to associate to such pair a probability measure supported in the product space Rn across capital N. Any. Of course, I will need some sort of measurable dependence, whatever. That would be a technical issue. But give me any rule to assign to every point in omega and every measurable function a probability measure in a consistent way. and then give me an integral. And then we can build this non-local functional down here. So I just integrate in the space where the support of this family of probability measures live. I integrate against this variable f over here, and then integrate again the outer integration is with respect to x. Okay, this is some functional. So every time I have such a rule mu, I have a non-local theory, and we could just identify this family of probability measures, some sort of non-local gradient, if you like, or whatever. So I'm placing myself here in a very general context. So my intention is that one can understand every non-local theory within this context. So depending on what your choice is of this mu, you will get local theory or a different local theory, or even the local classical theory would correspond to choosing, if u is, say, some sort of function, this rule will be just the delta function of the grad ux. And that would be a perfect rule under this umbrella over here. But of course, you can choose any probability measure whatsoever with support in the space, in the included space of matrices. All right. So let's just go back. So again, we have gone too high, and now we are going to begin to descend to the one-dimensional case. Just we can have a feeling, we can have a taste of what these non-local theories could be or could. So, as I said, the main two ingredients. I need a rule to assign probability measure to points and functions, and this is going to be my rule now. So this is a specific way of determining the rule I was talking about in the previous slide. So this is a probability measure. Phi is any continuous function. Okay, and notice that let's see. This is for each x. X in this definition, x is fixed, and integration takes place with respect to y. Okay, and take for instance the p power with p equals to 2, if you like, and therefore we are led to the functional I started with in this particular case. So the functional I started with in my second slide corresponds to this particular choice of this rule mu. Okay, all right. And of course, you can take the other examples I had for the non-local situations would correspond to those two integrals right there. So in some sense, I can identify the non-local gradient with this sort of quotient, and I'm going to call this the non-local derivative at x and y. And so my non-local functional, I can reinterpret my non-local functional in this way. Okay, and now I can look at these spaces, the natural spaces of functions, to where to study this functional with this non-local type of solid spaces, if you like, which in dimension 1, by the way, they are the same like the standard fractional solid spaces that you can find now in many places, even in books. For higher dimension, my impression is that it's something different, but in 1D, this non-local, this definition here gives you exactly the same fractional solid spaces, the standard fractional solid spaces. But never mind that. The whole point I would like to point out is this main property. Now, this main property is going to make a difference, because what I'm saying is that if I have a sequence uniformly bounded in these spaces with these are Banach spaces, you can assume that the norm is going to be the norm of the LP norms of those two objects. If you have a uniformly bounded sequence in those spaces, then you can find a limit. So what I'm saying is that a main property of these spaces is that if you have a uniformly bounded sequence in those spaces, then at least for a sequence, I mean, that sequence is precompact in LP, so that at least for a sequence you have you have a strong convergence in LP. For almost in almost every point. Once you have in almost every point, then these quotients, they would converge to the same quotient almost everywhere. So I believe that makes a difference in the sense that in the local case, you have this strong convergence in LP, but there is no way you can say about the grid. It will converge weakly, and you can go beyond that point. Here, because you have this strong convergence, and therefore, possibly for a further subsequence, a convergence almost every point, then you are going to have this convergence almost every point, almost every pair, or almost every pair in the product 0, 1 squared. And in addition to that, you will also have this with convergence. Okay. Now, that property is going to give me a very funny existent result without convexity. I do not need any convexity for this result. So if your integrand is continuous inverse U and capital U, and some measurability in X, and you have the usual coercivity condition with some P greater than 2 or whatever, greater than 1, definitely, then I'm always going to have minimizers in these spaces under prescribed endpoint conditions. But there is no convexity condition involved whatsoever. I don't know, at least to me, when I discovered this, as a consequence of the previous fact, it was a bit shocking because my intuition would tell me that some sort of convexity condition will be involved. And then say, well, just a second. For any continuous integrand, including, of course, the integrand for the Boltzmann problem, you are going to have minimizers. And then concerning optimality, optimality is going to be written in terms of some sort of integral equation instead of a differential equation. I suppose that's not so surprising because after all, well, I don't know. One never knows. If you look at optimality conditions for the local models involved in peridynamics, then you have some sort of you do not get an integral equation of optimality in the usual sense. It's some sort of non-local. You can generalize the divergence, the gradient, everything. Every differential operator you can generalize it to a non-local version of it. And therefore, formally, everything is the same, just as I was claiming at the beginning. But here, this is an integral equation, although it's not a typical integral equation, the ones you can find in books of integral equations of the first kind, of the second kind, and all of that. It's something different, because what I have here is some sort of integral equation. Notice that what I'm saying is that for almost every point x, this integration in y should vanish. And here there is some sort of non-local divergence, of course, I decided to call this some sort of non-local divergence just to keep formally the same with the usual optimality condition, but it's something different, as we are going to see. So anyhow, at least formally, these two results are correct, I believe. And the whole point again is that we do not have to export any convexity. And here we have some sort of integral equation, something, again, as I said, it's not a typical integral equation, but something. So what I'm saying is that if this U is a minimizer of the problem, then this should hold for almost every point. I don't know, it's something weird. So let me just, if I can count on these two results, let me just go to our two examples. So this is the integral equation of optimality in the principal value sense. One has to be careful about because these integrals are improper integrals, so they have to be understood in the principal value sense. And this is the optimality integral equation that you get for that integral up there. So therefore, we know that for the non-local version with this integral, there are minimizers because there are minimizers for every continuous integral. And those minimizers for that version of the problem would have to satisfy this integral condition, which says that for almost every point, all these integrals with respect to y should vanish. Those integrals understood in the principal value sense. And no idea about possible solutions of this equation. I don't know what kind of condition that imposes on a function u. No idea. But ux equal to x is not a solution. That's for sure. So therefore, the minimizer, which is the unique minimizer for the local version of it, is no longer a minimizer for the non-local version of this problem. Because if it were, then if you replace u by y and u of x by x, that should hold for almost every point, and that's certainly not true. So this is not the minimizer for the non-local version. But I cannot tell you what the minimizer is because I would have to solve this equation, and I have no idea what the minimizer is. Well, that's not quite solved. And the second point I want to stress is that there are minimizers for this problem. There are definitely minimizers for this problem, even though we don't have minimizers for the local version of the problem. For the non-local version, this non-local version of the problem, there are minimizers for this non-convex problem. And if you write down the integral equation of optimality for this is something like that. No way to come up with a function u for which this is an equality for almost every point where you are integrated here with respect to what. No idea what what this equation might mean. But I just went through some numerical approximation. And this is a picture of the minimizer for the quadratic case. So this is the minimizer for the local case, ux equal to x. This is the minimizer for the non-local version of it. This is a purely numerical approximation, which in this case is not that difficult. But the point is that we have to discretize those double integrals, right? It's not difficult. And you can imagine that I cannot claim to be an expert on numerics in any way. And yet I was able to succeed in coming up with this minimizer. And if you think about it, once you know that this is to be the minimizer, then if you think about it and what those double integrals mean, then you begin to realize that it makes a lot of sense, that the minimizer should be something like that. In particular, the slope at both endpoints is infinite. Because somehow the whole body is sort of pushing against the both fixed endpoints. And I also went through some other case with some inhomogeneous contribution. And then again, this is the difference. This is the local solution, and this is the non-local minimizer. The non-local minimizer. Of course, in all these examples, in the previous example, we lose the uniqueness, of course. In these cases, you have minimizer, but of course, there is no way you can have uniqueness. Because uniqueness, the only way we know how to enforce uniqueness is through strict convexity. And this is not even convex. So we have minimizers, but there is no way you can show that they are unique. And in fact, one would wait for infinitely many minimizers for such a problem. So let me just finish with a higher dimension, with a discussion of some higher dimensional situation. How one could try to push these ideas further, at least to deal or to treat a higher dimensional situation. So I start with an integral like that, depending. You can think of just W depending on F alone. Okay, so there is no need for more than that. And I would like to look at this function where capital X is living in n copies, in n different copies of omega. So this is something different from the beginning from peridynamics. For peridynamics, you just need 2 copies, right? Because you are sort of trying to understand the interaction between a couple of points in omega. Here I need this capital X lives in omega n over here. So I have n different copies of omega, and this capital X I can represent this by n variables, each one belonging to Rn. So therefore, this capital X is an n times n matrix, right? N times x matrix. And this derivative is going to be like this. Let me explain what this is, this subject over here is. So U of x is just the n by n matrix that you get when you just evaluate U at the n copies of the different variables, x1, x2, up to xn, like that, okay? So this is the this is Ux over here. So this is n by n matrix, which is whose columns is just the evaluation of your U at each point x1, x2, xn, and each one of those points are points in omega. Okay, and this black one over here, this is just a vector n, which is just made up of ones. All components are ones, okay? So that x tensor 1 is just n copies of the same vector x, okay? And so this matrix here is the tensor product of two vectors. One is U of x, and the other one is this vector 1. So this tensor product is just n copies of U of x. And therefore, this matrix over here is just this is a n times n matrix, like this one, okay? And this is a rank 1 matrix, which is written down here. So the difference is a n times n matrix, and this is again the same object without U. So here you have x, capital X, which is just all these different points living in omega, okay? And this is inverse. You have to invert this n by n matrix. This is a rank 1 matrix again, given here, okay? And the non-local gradient is going to be the product of this n times matrix times the inverse of this one. So this matrix here, written like that, you can think of it as the unique matrix taking the pairs. My goodness, this pointer is sort of special. So this matrix is the unique matrix taking this difference into those values. It's the unique n by n matrix taking these differences into these differences for every I from 1 to capital N. And I call that the non-local gradient or non-local derivative or whatever. And this is exactly what I've been doing in dimension 1. The thing is that in dimension 1, n is 1, so I just need 2 copies. Omega is just an interval, capital N is 1, and therefore I just need 2 copies. But as soon as you go to n greater than 1, For n equals to 2, you would need 3 copies of omega. For the integration up there will be in 3 copies of omega. If n is 3, then you would need 4 copies of omega up there. And so this will be the rule for this particular interpretation. It will be the rule assigning a probability measure to every pair x and u. You just take your field, compose with this non-local gradient, and integrate with respect to capital X over here. That gives you a probability measure, some sort of non-local probability measure, because the support of this probability measure will be all over the space of matrices with different densities, I would say, depending on your U. And with that rule, you can build a whole. I mean, you can build a non-local theory based on that sort of energy up there. Okay, and what I did was exactly this for the one-dimensional case. What I just showed you before is exactly this for the one-dimensional case. And in that case, even in those simple cases, the answers to many of these questions are quite different from the typical local case. And so almost everything remains to be understood in this more general context. Starting from what are the natural spaces. It's easy to write down the natural spaces where one would look for minimizers for such a functional, but it's, as far as I can tell, it's hard to tell whether those spaces would be something similar to something we already know. I haven't thought about that, so I don't know whether those spaces will be something different, or whether one could come up with the same spaces, the same non-local spaces. I doubt it. I believe that if you look at, if you just put here some sort of, if you replace W up there with some peak power and integrate some peak power of this non-local gradient, so to speak, with respect to capital X and little x, I don't know what kind of spaces you would get out of that. No idea. But those will be the natural spaces under coercivity conditions for your W. If your W has polynomial growth at infinity, the spaces you would have to look at would be those spaces, and I don't know what those spaces are. So that's something to be understood. And then other than that, one would have to start looking at again at Quasiconvexity and optimality conditions, and I don't know. I suppose that numerics for such models will be quite difficult to implement, because one would have to deal with even in capital N equals to 2, omega is a circle in R2, then we would have a triple integral in a circle. And I don't know, maybe through some sort of Monte Carlo methods for integration or something, one could come up with some numerics, I don't know. But essentially, for these sort of models, there are many open questions. On the other hand, I'm not sure whether, from the mechanical point of view, there will be some reasons to say something about this model, whether they could be useful in some sense, or whether this is just a purely mathematical object. I don't know. That's something that remains to be understood. So I think I will stop here, Martin, and thank you for your assistance and your patience. Thank you.